Today I'll be talking about binary lifting. So let's look at the problem. We have a tree and we want to answer queries of the form u comma v, where we have to find the LCA of the nodes u and v. So if we do a DFS for each query, this is too slow and we need a faster method. Now binary lifting is basically a technique that allows you to answer these queries in log of n, and there are multiple ways to go about binary lifting. The one I prefer to use is the one involving an Euler Tour. So I'll be first talking about those, and then I'll be getting to binary lifting. Then I'll be talking about minimum maximum queries as well as finding the LCA. And as far as the prerequisites go, there really isn't much. You just need to have a thorough understanding of DFS. And you might have heard that binary lifting is sort of dynamic programming on trees, but even if you don't think of it that way, it should be pretty easy for you to understand. And that's the goal of this video. So let me first talk about Euler Tours, because we'll be heavily dependent on those um, while we're binary lifting. Let me just draw a tree. Okay, so we have a basic tree here and it's rooted at this node. Now, the reason we use an Euler Tour here is to um, check for any two given nodes if u is an ancestor of v. And let's take a look at what ancestor here means. So for any node u, let's say this node, an ancestor of u will be any node lying on the path from the root to this node. So all these nodes are the ancestors of that node. Similarly, if we consider this node, then its ancestors are these bunch of nodes. Okay, so now to find whether some u is an ancestor of v in constant time, we perform what's called an Euler Tour. It's basically a normal DFS traversal. So we start from the root node, we go down. Now once we reach a leaf node, we backtrack and then we go back up. Then we go down again. And then we go back up. We continue this process until we reach the root node again. What we now do is we maintain some sort of counter variable. So every time we enter a node, so we start from the root, we um, save the time at which we entered this node. So for the root, let's say the counter is 0 and we increment it. Now we entered this node, we entered it at the time 1, we again increment it, and we go down here, we enter this, now we increment it. Now we went back up. So these numbers that I've written here, these represent the times at which we entered these nodes. Now we also need to store the time at which we leave these nodes. We don't have to increment a counter when we do that. So the time at which we leave this node is just 2. And then we haven't left this node yet. We're still going down. So we continue. Now the time at which we enter it is 3, 4. Now we leave this node. So the time at which we leave it is 4. We don't decrement or increment our counter. And then we go back up. We're leaving this node again. So 4. Go back up. We're leaving this node. 4 again. And now we're going down again. So our counter is incremented. Again, we leave this node, we go back up and we enter a new node. We leave it, we enter a new node, and then we go all the way back up to the root. So the numbers in red represent the time at which we entered some node, and the numbers in green represent the time at which we leave it. If you notice, you'll see that the times at which we enter any node is unique because we always increment it afterwards. Okay, so this actually gave us a lot of information about this tree. In particular, now we can actually check if some node U is an ancestor of node V in constant time. Let's see how we do that. Let's pick two nodes. Let's say we pick this node and this node. Now I want to check if this node is an ancestor of this node. Let's try to see what conditions must be satisfied in order for this node to be an ancestor of this node. And the information we have is the time at which we entered these nodes and the time at which we left them. So let's say that this node is U and this node is V. Time in of U is equal to 1. Time out of U is equal to 4. The time at which we entered V is 4, and the time at which we left it is also 4. We can see that U is actually an ancestor of V, but how do we check this? In order for U to be an ancestor of V, we had to have entered it before entering V. So the time at which we enter it must be less than or equal to the time at which we enter V. So it's smaller than equal to this. And now we also have the time at which we left these nodes. So we need to leave U after we leave V because it's an ancestor. So the other condition is the time at which we leave U is greater than or equal to the time at which we leave V. So these two conditions must satisfy in order for U to be an ancestor of V. Ready to get into binary lifting. So but in binary lifting, let me draw another tree. I've made this tree a bit long over here on purpose, and we'll see what we're going to do soon. So in binary lifting, the main idea is that for each node, you store its parents in powers of 2. By that I mean, let's have this table A cell in this table is basically the 2 to the power jth parent of node I. So if you look at this node at the bottom, and let's say j is equal to 0, so it's to the 0th parent, which is equal to 1, so the parent, the node above it, is the value stored in pair of I comma j if this node is I. That is basically, this is a 2 to the power 0th parent of this node. Now we again find the 2 to the power 1th parent of this node, which is here. Now 2 to the power second parent of this node, which is 4 nodes above it. And then we keep on doing this for each node. So in the end, what we want to do is we want to have computed this table for all nodes so that we can actually do some checks and find out the lowest common ancestor between two nodes pretty easily. So first, let's actually take a look at how we're going to compute this table, because if we, for every node, if we do a DFS and go up, that's too slow and it'll defeat the purpose of trying to find the LCA in a faster way. So the thing to notice here is that if we want to make 2 to the power x, this is equivalent to doing 2 to the power x minus 1 plus 2 to the power x minus 1, because that is basically 2 into 2 to the power x minus 1, which is 2 to the power x. So let's say we know the direct parent of this node and we know the direct parent of this node. It's pretty easy to compute. We just set the parents while going down the DFS. If we know these two things, then if this node is U and this node is V, then power of U comma 0 is equal to V. And let's say that this node is X. Power of X comma V comma 0 is equal to X. Now let's say we want to find power of U comma 1. As we saw here that 2 to the power x can be written in this way, we can also write this in that form. Since we know these two values, we can basically write what this is doing is we are first finding the direct parent of U, which is basically this, and then we find the direct parent of that. So in short, this can also be written as So instead of directly trying to compute this j, we've divided this into two ranges. We first find some intermediate node, and then we use information that we've already stored there to compute this larger jump. So this idea still holds for all values of j. So when we do a DFS reversal from the root, we'll already have calculated all the jumps we can make from these nodes. So if we're at the bottom here, then computing something like 2 to the power 1, it's just doing this and then doing that. Now if you want to do 2 to the power 2, if we use the 2 to the power 1 we've computed, so we go directly up to this node, and from here we do another 2 to the power 1, which we would have computed in the same manner we're doing this, which will be over here. And as you can see, 4 nodes above it, 2 to the power 2, which is 4, we would have computed that successfully. So now what can we actually do with this? Our queries are in the form of u comma v. Let's say that this node is u and this node is v. And we want to find the lowest common ancestor. So lowest common ancestor is basically, as the name suggests, the lowest ancestor of both nodes, the lowest ancestor of each node that is also an ancestor of the other node. So for these two nodes, their lowest common ancestor is the root node, because that's the only ancestor they have in common, and that's the lowest one. What we want to do is we basically want to divide this query into two parts. We consider the path from the root to u, this, and the path from the root to v. And we've divided this query into two vertical chains now. Now what we want to do is, we already know that we've already computed this binary lifting table on parents. So now what we can do is, we from u we try to make the highest jump possible. And what does the highest jump possible look like? So we try to visit some node such that that node is not an ancestor of v, and we want to make the biggest jump as the biggest jump we can at each step. So let's say we try over something above, let's say we had more nodes over there and we try that, which are ancestors of v, so those aren't valid. And let's say at some point we reach the our jump table points to this node, since it is valid and that's the largest jump we can make such that that node is not an ancestor of v, we make a jump and we're here now. Now we repeat the same process, and if you'll notice that at the end of this process we'll end up at the node directly below the lowest common ancestor. That means that the node at which we end up at, power of node comma 0, its direct parent, is equal to the LCA, which is basically our query, and so we can directly return that. Now there are two other cases to consider. When u is already an ancestor of v, or v is already an ancestor of u. If that is the case, we should simply return u or v according to the condition, because otherwise, since we're always returning the direct parent of some node, if u or v is already an ancestor, then it'll give us something else. And we already saw how to perform this ancestor check. So now let's look at some code. Okay, so I've defined some global constants over here, this is my graph, and this is the counter variable. Tn is the time of entering the node, Tout is the time at which we leave some node, and this is a binary lifting table where a pair of I comma j stores the 2 to the power jth parent of node I. So we have this normal DFS function here. This is doing what I talked about. So at the time at which we entered this node, then we increment the timer. After this, we use that recurrence to compute its parents. So we first find that intermediate node that we want to jump to. We divide it into j comma 1 and j comma 1. So after we found that node, we make another j comma 1 jump, j minus 1 jump. We find this node, we make another one, j minus 1 jump, and we do that for all values up till log of n. So max k here is just some upper bound on log of n. After that, we continue our DFS. So in this loop, we loop through the adjacency list. And now what we're doing is we're setting the direct parent of the node we're about to visit to the current node. After that, we go to that node and continue the DFS. Now while backtracking, this is the time at which we leave the node, and I'm doing timer minus 1 because we would have already incremented it here, but we don't want to increment the timer while leaving this node. Okay, now this is basically the function to check if u is an ancestor of v, and this is just the condition that time of entering u is less than equal to the time of entering v, and the time of leaving u is greater than or equal to the time of leaving v. Next, we have this query function. So like I said, we have to perform these two checks before, if u is an ancestor of v or v is an ancestor of u already. If this is the case, just return those nodes because that is the LCA. But if that's not the case, we want to be making the largest jumps we can possibly make. So we start from max k minus 1 and go all the way to 0. This is basically, we try to make this jump. If this parent is not an ancestor of v, and we want to make this jump because we know it's the largest jump we can currently make, so I just set the current node that we're at to be equal to this parent, and we continue this process, and in the end we'll end up at the node directly below the LCA. When that happens, we simply return the direct parent of the node, which is the LCA. This is taking input and answering the queries. I'll have this code in the description of the video. Thanks for watching. Make sure you like, share and subscribe if you loved the video. I'll also be listing a few problems you can solve for practice, and I'll see you in the next video.